Hello, everyone, and welcome to this Cyberseminar Series, Research and Observatory Catchments, the Legacy and the Future. We've had a great experience with this series so far. This is week 5, and we've had upwards over 100 participants every week. So thank you for your continued interest in this series. It's been really exciting hearing about all these catchments from around the world. CUAHSI is very excited to host this series, which was convened by Jamie Shanley, Stephen Sebestyen, Julia Jones, and Theresa Blume. My name is Julia Masterman. I'm the Science, Education, and Outreach Coordinator for CUAHSI. CUAHSI is the consortium of universities for the advancement of hydrologic science, Incorporated, and our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in water science at all levels through programs like this Cyberseminar Series. I would encourage you to reach out to me, visit our website, or sign up for our newsletter to learn more about what we do or to get involved. And the information to do that will be in the chat in a moment. This webinar series will be recorded and will be posted on the CUAHSI YouTube channel tomorrow. To check out previous week's recordings for the first few webinars in this series, visit youtube.com/CUAHSI. If you have any questions throughout the webinar, please put them in the chat. There'll be time for a brief Q&A after each presentation, potentially, but there'll be plenty of time for a longer discussion at the end. We'll do our best to get to as many questions as possible, and we look forward to hearing your thoughts during this discussion portion. This week's topic is low to no snow temperate and tropical catchments. And again, this is week 5. And with that, I'll pass it off to our convener, I believe, Jamie.
Yeah, I'll start out. Thank you. Thank you, Julia. So we have the map up next. So we've been presenting this catchment map each week with the current, this week's talks in red. There we go, that's this week, and the past weeks in yellow. So we're covering a good part of the globe here, and it's always fun to look at this map and see all the dots on it. So just want to make a quick plug for our week 8 coming up, where we're going to kind of brainstorm on the future of catchment research and your ideas. So we're soliciting ideas. We're going to present a more formal way for you to give us ideas on how we want to structure that. We have some that we might put up as a straw man, but look forward to that. Today, Theresa Blume is going to be moderating. I'm just starting out here to introduce her. She's also the first speaker. I want to give the floor quick to Steve to tell how we're going to handle the questions today. Steve.
Thank you, Jamie. Welcome, everybody. Like Julia and Jamie have mentioned, we want interaction. We're really looking forward to you asking questions for the panelists, specifically about their individual presentations, as well as for the discussion at the end. So please keep your thoughts rolling. Enter it in the chat window. Audience members will not see what individual audience members put in. The panelist will. We ask the panelists to re-enter the question, then give their answer if they give an answer via the chat. But please do it throughout. Just keep the questions coming. What we don't get to after each individual speaker, we hopefully will pick up either later on in the chat or during the discussion at the end. With that, Jamie.
Okay, so Theresa Blume has been one of our conveners here. She's a chief executive editor at Hess, and she has the first talk today. So after this, she'll be moderating, but I'll introduce you to Theresa now. Go ahead, Theresa.
Thank you. Yeah, I will be talking about the TERENO network, or more specifically, one of the observatories in the TERENO network. Next, please. The TERENO network is a network of terrestrial environmental observatories funded by the Helmholtz Association. We're there studying the regional impacts of global change in 4 different observatories in Germany. Each of these observatories is run by a different Helmholtz center. Next, please. Today, we'll be focusing on the one in northeastern Germany in the Lowlands, which is run by GFZ. As you can see on the map, it basically consists of several different sites. For example, at the Demmin test field, people are looking at ground truthing of remote sensing products. Then we are looking at several wetlands in terms of greenhouse gas fluxes and microbial communities. At Lake Tiefensee, The paleoclimatologists are studying varved lake sediments, and we hydrologists are mainly focusing on the Müritz National Park in the middle. Next, please. For some background, this region in northeastern Germany is actually quite vulnerable to climate change because we have quite low rainfall amounts. And you can see the effects here in the declining lake levels. This is the situation as it was in 2010 when it was particularly bad. Next, please. So our observatory is located here in the German Lake District. And if we zoom in, next, please. You can see that the catchment of this lake is basically all forested. We're looking at quite a few different plots, different forest stands, different tree species. We measure a lot of different variables, as you can see in this list here, that's not even complete. And to move on to the next slide, please. Our research questions focus more or less on the one hand, on forest impact on hydrology. This includes how different tree species affect interception and stem flow. Then how this affects subsurface flow processes, both in the unsaturated and the saturated zone, also the storage dynamics there. And then it moves on to the interactions of groundwater and surface water. On the other hand, we're looking at forest resilience, basically through dendrometer measurements of tree growth and sap flow, but also root water uptake. And we also develop and test new monitoring methods. Next, please. Just to give you an idea of the different data sets we're collecting, or just some examples here, sap velocities or sap flow for beech trees in the summer of 2018, which was particularly dry. And you see the strong decline in sap velocities over the course of the summer. Next, please. So the gray lines are...
You're just at 3 minutes.
Okay. The gray lines are the upslope trees. And if you compare now to the red lines, the downslope trees, you can see how different the responses are. Next, please. Looking at tree growth, the high resolution measurements from our dendrometers, you can see here time series from 2012 to 2019, and the different colors show averages for different tree species, pine, oak, and beech. And you can already see on first sight how different these tree species respond to different conditions throughout the years. Next, please. We also want to put our current observations in the context of longer timescales, and we do this on the one hand through dendrochronology, where our dendrochronologists not just look at tree ring width, but they go down to the cellular level. We also use reconstructed lake level dynamics for the past millennia to put our current observations of these dynamics in this context. Next, please. We also have a few more unusual types of equipment, such as, for example, this gravimeter. The gravimeter measures the dynamics of gravity at our site, and this can be related to water storage dynamics. And here you see a time series from fall 2017 to fall 2019, and you can see the strong decline in water storage. We also use additional methods for integral soil moisture measurements, such as cosmic ray neutron sensing and GPS reflectometry. Next, please. And as I said, we also study how the groundwater interacts with the surface water, and here, more specifically, the groundwater discharge into the lake. We found that the discharge patterns are spatially highly variable, but actually quite persistent in time. Next, please. To conclude, just a bit of an overview of our challenges, struggles, and successes. On the challenges and struggle sides, well, we're still struggling with QA/QC workflow, data management, data publication is going a bit slow. We of course have data gaps, struggle a bit with funding, and then struggle with the dry conditions these past years. Also, we have quite some interesting results that are still waiting to be published. It's going a bit slower than we would like it to go. On the success side, the sites are still running. We're testing cool, novel monitoring methods. We have many ideas. We have a good working relationship with the national park, which is really, really valuable. And we have many interesting results that are waiting to be published. Thank you.
Thank you, Theresa. I think we need to move on to our next speaker.
Yes. Our next speaker will be Beth Boyer. The floor is yours.
Hello, everyone. I'm here today to talk about long-term observations at the Leading Ridge and Shale Hills watersheds in central Pennsylvania, USA. I wanted to acknowledge my colleague, John Duncan, who's been working at the Leading Ridge watershed since he joined Penn State a couple of years ago, but also importantly to acknowledge contributions from many, many others who've worked at these sites over the years. Hundreds of people over more than 60 years of long-term observations. Next. So the Leading Ridge and Shale Hills watersheds are located in the Ridge and Valley physiographic setting of central Pennsylvania. Shown in the red star are a set of 3 watersheds that I'll talk more about in a subsequent slide, the Leading Ridge, that are representative of the ridge. Then there's also the Shale Hills experimental catchment that's representative of the valley, essentially a hill in the valley. And these catchments were started in 1957 to be representative of the huge swath of the eastern United States that's in the Ridge and Valley setting. These are forested watersheds underlain by shale and sandstone. Next. The Leading Ridge watershed unit consists of 3 experimental watersheds that are still observed today that have been in observation since 1957. There's the watershed on the right, Leading Ridge 1, which is the control site. And though it's been relatively undisturbed in terms of no treatments, it has seen disturbances such as gypsy moth defoliation, floods, droughts, and so on. The other 2 watersheds have been treated, and I'll talk more about those in a subsequent slide. Next. At the watersheds, the Leading Ridge, the Shale Hills, and other regions of the larger watershed called Shavers Creek in which they sit, there's been a host of long-term measurements made and short-term measurements made in recent years. The watersheds, the Leading Ridge watersheds and the Shale Hills all were instrumented with different kinds of weirs. Stream flow measurements have been going on for since the 1950s. There's also precipitation measurements that are available since then. At some locations, there have been up to 10 different places within the watersheds where precipitation rates have been measured. There's also been measures made of soil characteristics, soil chemistry, land-atmosphere interactions, eddy covariance, atmospheric deposition rates, chemistry, soil moisture, geophysics, deep wells drilled with well chemistry and lithographic information available, all sorts of characterization of surface water, precipitation water, and subsurface architecture and chemistry. Next.
You're just at 3 minutes.
Next slide. So the watersheds have been used over the years to explore an evolving set of questions, starting with things like the role of forest management, stream flow generation mechanisms, investigating the role of atmospheric deposition, acid rain, the Clean Air Act amendments of 1990 and how those have changed things, vegetation and ecohydrology responses, water quality, climate variability and change, and a whole suite of critical zone processes. The Shale Hills site was designated over a decade ago as a critical zone observatory where there's been an influx of new measurements really characterizing for the first time a deep time and critical zone architecture of the subsurface that added a huge amount to the new research questions at the site, thinking about evolution over long and short time scales. Next. Relevant to next week's topic, I believe, or another in the series coming up, these watersheds, the Leading Ridge watersheds, some of them were subject to forest management treatments, where one of the watersheds was left as a control. One of the watersheds was completely clear-cut and removed of all vegetation with a combination of clear-cut and herbiciding in 3 phases. First the lower third, then the lower third plus the middle third, then the whole catchment, as shown in one of the illustrations in the lower left here, the figure. And the other basin was treated with thinning and the use of best management practices to explore the role of BMPs in their impacts on water temperature, water quality, and water volumes. Next. One of the things that we've been doing is trying to reconstruct the long-term record of flow at these sites by digitizing literally a whole room full of strip charts. So I can't underestimate the work that goes into reconstructing a long-term record like this. Myself, John Duncan, and others have been working on this and have recently just completed understanding the long-term flows at this site from 1957 to the present. And so this slide just showing leading ridge watersheds 1, 2, and 3, and their general water balance, that is the control and the treatment watersheds, and their general water balance over time. On average, about 45% of the annual incoming precipitation is delivered to stream flow, and they get about 1,000 millimeters of rain per year. Next. Another important thing that makes these sites such a wonderful test bed is the fact that atmospheric deposition in the eastern United States has really changed over the years due to policies, very successful policies that have decreased emissions of nitrogen and sulfur oxides to the atmosphere. Just to illustrate, precipitation at the site, about 41 inches of rain per year, is naturally trendy. We have a lot of flood and drought periods in any period of time, but it hasn't really trended up or down. But in response to management, atmospheric deposition concentrations have come down in terms of sulfate and nitrate. So a lot of the recent work is focused on ecosystem responses to this sort of change. Next. And most recently, this site has part of the new, the Critical Zone Observatory funding has just ended, and the slide that has just whizzed by has described where you can find all of the data from these catchments. So this is an important site because it has the contacts and the data availability. Thank you.
Okay, thank you. We will have to move on quickly. Sorry about that. So our next speaker is Daniele Penna. Daniele, the floor is yours.
Hi, everybody. My name is Daniele Penna from University of Florence in Italy. Thank you very much to the organizer for the opportunity to talk about this new experimental catchment in the Apennine Mountains in central Italy. And this work was basically done by my university with the collaboration with the University of Padua in Italy and the Luxembourg Institute of Science and Technology through a joint project. Next, please. So why do we want a new experimental catchment in forest environments? Well, we all know that climate and land use change are strongly modifying eco-hydrological processes and their associated ecosystem services in forested catchments. And understanding the feedbacks between water and forest in forested catchments is critical and is getting even more important for sustainable management of both water and forest resources. And moreover, from a more practical point of view, there was a lack of experimental catchment in forested areas in the Apennines. And this kind of environment is a kind of bridge between alpine areas and catchment and southern Mediterranean sites. Next, please. So the main objective we are trying to address through this experimental catchment is trying to get a better understanding of the hydrological and eco-hydrological functioning of forested mountain catchments in the Mediterranean basins. And we try to address this overall objective by looking at different points. For instance, we are analyzing the temporal and spatial origin of runoff components, mainly through tracers analysis. And we focus on the role of the seasonal forcing, especially during possibly dry summer, and evapotranspiration fluxes on stream flow generation. We are looking at the spatial and temporal variability of throughfall at the Hislop scale in this densely forested catchment. And then we are also addressing more eco-hydrological questions, mainly related to the role of topography on the water sources used by forest trees, and also the hydrological controls on the physiological response of forest trees. Next, please. The catchment is located in central Italy in the Apennine range, so the elevation is relatively low, between 100 and 1300 meters above sea level. And the region is the beautiful region of Tuscany. The main geology there is limestone, and so it's relatively permeable systems, and this is probably interesting from a hydrological point of view. And the forests basically cover all of the area, or almost all of the area, with different trees and different species. Next, please.
You have just about 2.5 minutes.
Sure. So I'm not showing any results because we started to instrument the sites basically 2 years ago or something like that. And we are following a nested approach. So we are measuring water fluxes through a string gauge at 5 different locations, from the upper sub-catchment that you can see outlined in pink. And then we have about 0.3 square kilometers, and then we go downstream down to the catchment outlet of about 2 square kilometers. And then here we are, in addition to discharge, we're also measuring the main weather parameters. We have 3 rain gauges at different elevations, and we are measuring soil moisture at different depths in different parts of the catchments. And we are measuring throughfall through manual grid, groundwater levels. And then we also have some eco-hydrological measurement related to specific trees. We're measuring the radial growth of trees and the Sapflow fluxes, and the stem humidity and the light transmitted through the canopy. On top of that, we are taking isotopes from basically several water sources, including precipitation, stream flow, groundwater, spring water, and soil water and xylem water. Next, please. These are just a few overview of the catchments. On the upper left corner, you can see the grid for manual throughfall measurements. And there are soil moisture probes in the steep sea slope in the upper part of the catchment, different section for stream water level and groundwater levels, and tracers analysis, in this case from the soil. And then in the green circle, you can see a tree talker, which is a kind of innovative multi-parametric sensor that actually records all the different parameters as a dendrometer, subflow, and stem humidity, and light transmittance. Next, please. But I think that's basically all. And so no data so far. We're still basically equipping the sites, but I hope you will hear more about the Re della Pietra catchment. Thank you very much for your attention.
Thank you, Daniela. There's no questions for you yet. There are some questions and responses being posted for the previous panelists. So stay tuned there, everyone, and keep the questions coming.
Thanks.
Okay, thank you, Daniele. Our next talk will be by Tomas. The floor is yours, Tomas. I think if you're speaking, you're still muted.
Did we lose Tomas from the session here?
No, we didn't.
Oh, good.
So let me give you a quick tour around Lesni potok catchment, located in the Czech Republic in the heart of Europe. Next, please. Before I start, Lesni potok is a part of GeoMon monitoring network, which was founded in 1994 and was designed to assess the effects of acidification on Czech forest ecosystems. The acidification in the end of 20th century was the major environmental problem in the Central Europe and Czech Republic. These 14 catchments are managed by Czech Geological Survey, and Lesni potok, located right in the middle of the country near Prague, is run by the geochemistry group at the Institute of Geology of the Czech Academy of Science. The catchments are monitored with monthly step. We sample bulk precipitation, truefall, and stream water solutes. And recently we also added litterfall. Next, please. Next, please. So some details about Lesni potok. It's underlain by granite. There are district cambisol as a soil cover, and the forestation is 1:1 ratio conifers and deciduous species. It's about 3/4 of a kilometer square, and it's located in relatively low elevation at 470 meters. The precipitation, the annual precipitation is about 600 millimeters per year, and the stream runoff about 100 millimeters, which makes the evapotranspiration rate at this catchment very high, over 80%. Next, please. Here, I'd like to draw your attention, next please, to the autumn months, where there is low to no discharge at Lesni potok, and which is not typical for the other 13 catchments in Geomon, but our modeling using some regional climate models indicated that this is the way that some other forest catchments in the Central Europe will behave like in near future. Next, please. Now I will express some of the achievements we made at the Lesni potok. So back in 2004, we were able to report to the public and authorities decline of lead deposition due to phasing out the leaded gasoline in the Czech Republic. Next, please. The Geomon catchments were also modeled using acidification and recovery prediction models, which predicted recovery, which you can notice on the left side top panel, stream water pH increasing in the past 20 years, sulfate concentration decreasing due to changes in deposition. That's all good news, but on the right side panel, not very good predictions for recovery of the base saturation, of soil base saturation, of mineral soil. Next, please.
You have 2 minutes.
Yep, thank you. We also focus on elemental budgets. So in this study back in 2007, we identified, next please, a major fluxes of manganese in the forest ecosystem, but we also noticed the substantial amount of export from the catchment. This was in contrast to, next please, to the elemental budget of mercury, which is being studied recently at all the Geomon catchments, where the export rate, as you can see, is quite low. So this gives us idea that the toxic mercury is actually accumulating inside of the forest ecosystem. Next, please. Okay, next, please. And next, please. So to close down, the research focus at Lesni potok and at the whole Geomon network is shifting from the monitoring of acidification and recovery phenomenons to the response of forest ecosystem to climate change and associated effects, such as long periods of droughts that we experienced, and also forest dieback due to bark beetle infestation, which is a big issue recently in the Central Europe. We are also building a soil database for all sites. Thank you, that's all.
Thank you, Tomas. I think we're going to move on to the next presenter.
Thank you, Tomas. Our next presenter is Rhett Jackson.
Thanks, everyone. Today, I have the pleasure of representing the Coweta LTER and the Coweta Hydrologic Laboratory. At Coweta, we have a long history of conducting large-scale and watershed-scale experiments. and of coupling ecosystem and hydrologic observations. We operate under the philosophy that long-term data can basically give us insight into things that short-term data can't, and can often reveal some interesting surprises. Next slide, please. So in 1976, we clear-cut Watershed 7, and in that left graph, you'll see the deviations from the expected stream flows on the y-axis and the deviations from the expected dissolved inorganic nitrogen concentration streams on the x-axis. And at first, things did what we expected, that after we clear-cut, we saw both stream flows and DIN increase as ET and mineralization decreased. And then things continued to do what we expected. They started to return to pre-harvest conditions. But then the unexpected happened. Then we saw basically 20 years of long-term increases in dissolved inorganic nitrogen. Now, we did not expect that. And it led to follow-up work by forest ecologist Nina Wurzberger, who went around. What we noticed after we clear-cut this, that the young stand was dominated by nitrogen-fixing black locust. But after about 20 years, the black locust started dying out. Well, Nina went around and did surveys of nitrogen nodules in the forest, and she did a chronosequence to develop these models that show biological nitrogen fixation by the black locust over time after disturbance. And what we see is that the nitrogen fixation has a time frame of decades, that for 2 or 3 decades following disturbance, you're going to get higher nitrogen inputs, and we see that in the stream. Next slide. So in the 60s, John Hewlett, the hydrologist, built a series of controlled soil models in the hill slopes. And he did this to conduct experiments to illuminate some ideas about interflow support of base flow, about soil moisture redistribution on hill slopes, and about the variable source area concept. Next slide, please. Well, after 50 years, his 14-meter soil model had 50 years of leaf litter falling on it, and it had trees growing in it. And in about 2015, we said, did those mixed sea horizon materials that John Hewlett put in the trough develop horizonation? Did we see soil development? Did the macrophore development affect outflow rates? And so, next slide. We redid his experiment. And first we took soil cores, and the soil cores showed us, yes, 50 years had caused soil profile development. We saw lower bulk densities in the upper soils, higher bulk densities in the deeper soils. We saw organic matter accumulation in the soils. We saw incipient A horizon development. And most surprisingly, we saw a big shift in the soil textures. They started out as sandy clay loams. And when we got to them, they were basically silt loams, that a lot of the sand particles had weathered to silt particles. So next slide. We redid his experiment thinking that all that soil development and macropore development would change the outflow rates. So the first surprise we had was that for the first 10 days of drainage, the outflow rates we observed were indistinguishable from the outflow rates that Hewlett observed in his original soil model. But the caveat is that the concrete had developed a small leak in the lower part of the slope. And that slow leakage rate completely changed our inference about interflow support of base flow. So what happened was, as Hewlett observed this trough flowing for more than 140 days after he wetted it up, ours stopped flowing in 12 to 17 days, mostly 11 and 12 days. That small leakage to groundwater, to bedrock, which is more realistic of what happens on these slopes, very much changes our view of whether shallow interflow can support base flow. And it tells us that the base flow support in these mountains is still from groundwater flow. Next slide.
You've got about 1.5 minutes.
Okay, thanks. So, can you get this slide full? I didn't know it was in pieces. Thanks. So another thing we observed is that processes with different timescales may have different trends. So for example, we've got this long-term record where we see that net primary productivity has been increasing, and that we've had increasing leaf litter carbon and nitrogen fluxes to the ground. Can you advance, Julia? But we don't see any trends in soil carbon or nitrogen, that the soil carbon and nitrogen pools are so large and the data are so noisy, you don't see that signal coming in from the canopy. Next slide. Another thing we've learned at Coweta is that the past is not the past, that we did not start the site on low disturbance virgin forest, and that there have been a whole many changes in land use and disturbance over time, the effects of which we still see in our records today. Next slide. So one of the things I think we really need to think about in these study watersheds is that we need to explore spatial variability in groundwater behavior. Most of our study catchments don't have enough wells. Another thing I'd suggest is that we actually do experimentally seed some of these long-term catchments with contrasting conservative and non-conservative tracers and quantify travel times over decades. And finally, I'd suggest that we look for any evidence of downslope water subsidy of ecosystems in planar hill slopes, because I would argue that mostly what we've seen is that subsidies occur where you've got discontinuities in either the geology, the topography, or the soils. Thanks very much.
Thank you, Rhett. I think we're going to move on to the next speaker. Do keep
Yes,
the questions coming. We are having some of them answered in the background here too. So thank you for everyone who's interacting that way.
And our next speaker is Todd.
All right, thank you. I'm presenting on the Virginia watersheds. Next slide, please. So the motivation for what we do can be shown by this figure right here, showing sulfate deposition, what it looked like back in the mid-1980s, compared to what it looks like now. And so we're asking questions about what have been the changes in stream chemistry during this time of recovery from acid deposition, and how does it affect the watershed biogeochemical processes? So that's kind of the main question that we ask. We ask others, but those are driven mostly by our long-term funding, which comes from the EPA and the National Park Service. Next, please. So those questions dictate what we measure. So with every water sample that we take, we measure base cations, acid anions, and other properties like pH and acid neutralizing capacity. On a subset, we measure aluminum, ammonium, DOC, and then depending upon projects, we've looked at mercury has been a focus of ours, have time series of dissolved oxygen, and more recently, we've started to look at microplastics in the water. Next, please. So our sampling strategy, it's a stratified strategy. We have a large number of streams that we sample every decade, more limited number, 66 streams that we sample on a quarterly basis, and then 4 streams that we sample on a weekly basis. Those all have discharge measurements. 3 of those sites have episodic sampling. Next, please. So the decadal sampling we've done 3 times already. We were scheduled to do it last year. That got postponed because of the pandemic. We're scheduled to do it next month in April. Again, large number of streams, 456. We enlist trout fishermen and women to help us collect all those samples. And it's a great way to keep them informed about the science that we do. Next, please. For our quarterly sampling, we have 66 sites. Those are shown in red here. We're part of the EPA's long-term monitoring program. Next, please. So this kind of summarizes what we found from those 66 sites. So each of those arrows that you see here represents the trajectories that we measured within those 66 watersheds. The first thing that you can see is this relationship between pH and ANC. There's the influence of bedrock. So silicic classic watersheds tend to be the most acidic. Those have the lowest ANC values and lowest pH values. The arrows, the starting point of the arrows was the conditions back in around 1990, right at the passage of the amendments to the Clean Air Act. And then it shows where it ended up more recently. In general, what we're seeing is this phenomena, the rich getting richer and the poor getting poorer. So the sites that were doing pretty well back in 1990 are the ones that have seen by and large to get better. The ones that were struggling, like if you look at the lower left-hand corner, those silicic classic sites are actually getting worse. We know from magic modeling that they should have been at around 60 to 90 microequivalents per liter in ANC pre-industrial. And really haven't moved much in the last 30 years. The recovery has been a lot slower, actually, than has been predicted by models. Next, please.
You have 2.5 minutes.
Okay. We've done some synthesis work recently, and this involved collecting data for sites similar to our 4 sites that you see in Virginia right there, where we have weekly chemistry data and discharge data. So we're kind of thinking to ourselves, what sites have similar data. So I kind of wish we had this symposium leading up to this effort. But you see a lot of these sites on this map are ones that we've heard from in this symposium series. So we collected data from these sites who are willing to share their data, and we did mass balance on this. Something kind of neat that appeared from this is if you look at the flow normalized concentration of all those northeastern sites for sulfate, it seems to have converged onto pretty much the same sulfate values in recent times. There's the one outlier, that weird site is Jamie's Sleepers River site that has an internal geological source of sulfur. Next, please. If you add the southeastern sites onto this, they're all over the map in terms of the sulfate concentration and trajectories. Deposition of sulfate has decreased 85, 90%, and yet the trajectories in some sites are increasing or staying level over that same time period. So that really shows the dominance of local soil processes with the absorption and desorption of sulfate. Next, please. One of the nice things that we have at several of our sites is episodic sampling, a long-term record of episodic sampling. We have ISCOs that are triggering during storm events. And the story that it tells for base flow conditions versus storm flow conditions is somewhat different. So if you look at the pH time series for Pain Run, a little bit of improvement over the last 30 years. Next, please. But if you look at the high flow, the improvement is much more rapid. So it tells a better story with the high flow pH. And that differential has diminished over time. Sulfate kind of showing the same thing. It's decreasing over time. Next, please. But if you look at the high flow sulfate concentrations, they're decreasing even faster. So in terms of a CQ relationship, you get this flipping from flow activation to flow dilution over the last 30 years. And just as a question I'd like to throw out there to other people who are aware of sites, are there any other sites that have such long-term high flow chemistry measurements? So we're just kind of interested in synthesis opportunities. If you're aware of a site, if you could enter it into the chat, I'd be interested in knowing about those sites. Next, please. We're part of the HB special issue, and so that should be coming out. Our data is available for the public, and the last slide had shown where to access that. I'm out of time. Thank you to all those people who have worked on the project. Next slide, please. Over the years, including the people who started the project back in 1979, and thank you to the people who have supported our research financially. Thank you.
Okay, thank you. Now we're moving on to the tropics. And our first talk from the tropics will be from Josh West.
Hi, everybody, and thank you very much. I really first want to thank everybody who's been putting the hard work in to convene this series and everybody who's contributed. I found it really enriching. I'm really happy to move us into the tropics, and I should preface what I'm going to talk about with a little bit of a sort of statement of that I feel a little sheepish presenting this, in the sense that it's the contribution of a great number of people, as many of these catchments are, and it's also relatively immature compared to the data sets that so many of you have produced, right? So we're working in a region that I'll describe some of the challenges of as I go on in the next few slides, but it's certainly one where we're doing our best to add some data from a part of the world that's not easy to get to, but that I think is very important. But we don't have the kind of rich data sets that many of you have, although we're working towards it. Next slide, please. So where I'm going to take us is to this study site in the Madre de Dios Basin, which is in the eastern flank of the Peruvian Andes in sort of southeastern Peru. It's a few hours outside of Cusco, which is in the map on the bottom left, towards the southwest. This region spans the elevation gradient from Andean peaks at about 4,000, a little higher than 4,000 meters, down into the lowland Amazon basin, as you can see in this diagram. And we've been working kind of across this whole gradient. Next slide, please. Our motivating questions across this have been ranged from basic questions about catchment hydrologic and biogeochemical function, particularly thinking about those across a mountain to floodplain transition, and the regional significance of those, as well as the global implications. This is a region that, if you think about the sort of classic Humboldt vegetation gradient in the tropics, this is sort of a stereotypical example of that. We range from lowland rainforest at the low elevations up through tropical montane cloud forest into puna grassland ecosystems at the highest elevations. Of course, there's snow in some parts of the Andes. In this catchment, there's very little snow, and in the catchments that we've been studying, there's no snow. So it's an interesting opportunity to work in a mountainous environment with many, certainly the Andean portion has many of the characteristics of alpine catchments without the snow part of the story. I find it also a fascinating place to work because it gives us a chance to really understand the hydrologic role in sustaining the ecosystems of the Andes Amazon, which I imagine many of you have some familiarity with, right? And these are ecosystems that we know to be very hydrologically sensitive. So lots of questions about the future of the Amazon in terms of hydrologic response, and here's a chance to study those. And the last thing that I'll point out in this image from Google Earth that I think is particularly interesting about this region, and I'll talk to you a little bit at the end about this, is that there has been quite a bit of disturbance in part of the Madre de Dios Basin. It's probably best known in the environmental science world for all of the artisanal scale gold mining that you can see the imprint of in the sort of bottom left of this image. And that's come with a lot of mercury pollution. So this has been a kind of poster child for mercury pollution associated with small scale gold mining in the Amazon. Next slide, please.
You have 2 minutes.
Okay, I'll speed up. Next slide. A lot of meteorological monitoring has gone on. I'll talk in a moment about some of the challenges that are associated with that. But just to point out, we get very high rainfall in this region, ranging up to 5 or 6 meters per year at the mountain front. It tails off both at high elevations and at low elevations. Next slide, please. We've done work to pair that meteorological monitoring with stream gauging, including water budgets and isotope partitioning in the Andean portion. I encourage you to have a look at this paper if you're interested in it. Really interesting seasonal dynamics that come out from this analysis. Next slide, please. We've also done a lot of work on concentration discharge dynamics. We've done this across scales, from really large scale across many thousands of square kilometers, where the concentration discharge relationships are dominated by mixing. We've done more recent work, which we're working up at the moment, on smaller catchments at less than a kilometer squared, where the dynamics are somewhat different. Next slide, please. A lot of our effort has also been on understanding the sourcing, transport, and to what extent solutes and organic materials transformed across the floodplain. So we've sampled at all these sort of points that you see here to try to trace material as it's transported across the sort of immediate foreland floodplain delivered from the Andes. Next slide, please. Our recent focus has been on these small catchments across this gradient. I don't have time to talk in detail about them. This is stuff that we've just been wrapping up prior to the COVID pandemic. I hope that we can get some data out there in the coming months to year. Next slide, please. Yeah, and I'll just point out that, again, going back to this idea of, I have a proposal submitted and pending review to explore more about the hydrologic response to this disturbance from gold mining, because it's been a difficult region to access in the past due to safety, but that's changing. So thank you very much, and appreciate the chance to talk about it.
Thank you, Josh. Our next talk will be by Jean Riot. Jean, the floor is yours.
Thank you, Theresa. I will present you the Entropic CZO network, which aims at understanding the response of tropical experimental catchments to global changes. Next, please. So as you can see on this map shared by Jamie and Stephen, there are very few experimental catchments located in the tropics, although these regions face fast land use changes. They are also fed by monsoon systems, which are characterized by long-term variability and extreme events. And the tropics also enhance water-soil plant interactions that lead to high water and biogeochemical cycles to the ocean. Next. So the question we want to address is what are the solute, water, and particulate fluxes exported from tropical catchments? And in particular, what are the impact of the rapid land use changes on these fluxes? Next, please. So the Tropics was set up in 1994, and we built over time 6 experimental catchments across 5 countries, and through a gradient of climate, bedrock type, topography, and land use. And today I will present the 3 sites for which we have submitted data notes. Next, please. The first one is the Nyong Basin in Cameroon, which started in 1994. So the setup consists in 5 nested catchments from Order 1, which is a semi-small experimental watershed of 0.6 square kilometer. And the biggest one is the Nyong Basin, 20,000 square kilometers. And our objective was to understand the evolution of watering fluxes and CO2 consumption regarding climate change in a pristine, humid tropical forest. Next, please. The second site is Waipano, was set up in 2001, so it belonged to Lao PDR. And here we focused on the evolution of erosion in mountainous subhumid conditions, and particularly regarding the evolution of land use, shifted cultivation, and climate change. This experimental watershed is also 0.6 square kilometers. Next, please. Next. The third one is Muleole in India, and this one aimed also at looking at weathering fluxes, but in a dry deciduous forest, which means that this watershed has a very ephemeral stream, and making an hydrological budget there is quite challenging. Muleole is 4.1 square kilometers, and it is pristine, located in a sanctuary. Next, please. For all the sites, we measure various variables, so weather, hydrology, particularly stream and groundwater levels, geochemistry, and land use when needed. And you have some illustration about the conditions we are working in, so which are close to those of Joshua, I think. So sometimes basic, sometimes remote places. In the Nyong Basin, you can see the primary forest, and just on the left, the Dunsimi outlet with the black waters. At the Waipano, you can see the suspended sediment sampler and also the color of the water, highly turbid. And in Muleole, the dry outlet, most of the year with a flash flood. Next, please.
You have about 2.5 minutes.
Thank you. So all these watersheds experience evolution over the time we made observation. And in Cameroon, we have observed a long-term evolution of the stream chemistry, but we still do not know whether it is due to the change in hydrological regime because the monsoon shifted from a double season to a single one over the last 50 years, or if it's due to a change in vegetation dynamics, particularly an increase in local slash and burn agriculture. Next, please. In Waipano, we observed in the recent years a massive soil erosion due to the conversion of tropical crops to teak plantations, to the point that we now observe landslide and it becomes difficult to even collect the bedload. Next, please. In the Muleole forest, we observed that the tree really optimize on decennial scale the water stock and dynamics in the thick saprolite, and the vegetation also control directly but indirectly too the water and solute exported by the watershed. Next, please. So we are open to many collaboration, and for instance, about the role of headwater catchments in large tropical river basin hydrology, or the impacts of climate and land use changes on catchment dynamics, but also for monitoring new variables or be involved in modeling. You can find more data and information on our website. Please visit it, or contact directly the people involved in this observatory, either those in the countries or the French one. Next, please. On behalf of this team, thank you very much.
Thank you, Jean. We have to move right on to the last talk for today, where Bill McDowell will take us to Puerto Rico.
Thank you very much. As you can see on the map on the upper left, Puerto Rico is the smallest of the Greater Antilles, is about 1,600 kilometers south and east of Miami, Florida. And we study in that yellow circle, the northeastern corner of the island, which if you look over to the right, looking up from the beach to the island, to the mountains, is a steep volcanic massif that's rising pretty much right up to the sea. So we don't really have large floodplain connections between us and the sea, unlike our previous very interesting talks about the Andes. Next slide. So looking at the experimental forest catchments over the years, there's about 10 that we studied. The number has waxed and waned a little bit. They're all warm, temperature of 22 degrees. They're all wet, average rainfall about 3.5 meters up to 5 meters on the mountain peaks. All tropical, of course, on the same little island, 18 degrees north. They're very steep channel slopes generally, with some exceptions. A deciduous evergreen forest, and very modest seasonality in rainfall and litterfall. Next slide. So an important aspect of the site is that we have two different lithologies. We have this plutonic quartz diorite, which is up in the upper right. It's recently been termed a tonalite, but basically a granitic, and then a volcaniclastic. And so the volcaniclastic is pictured in the two images across the bottom. We have some really interesting bedded materials, and we get some very dramatic waterfalls in the volcaniclastic landscape. Next slide. So the first lesson we've learned over the years is that hurricanes, the big disturbance of hurricanes, induces large nitrate pulses in stream chemistry. And so the hurricanes, we've had 3 in the last 30 years that are category 3 and greater and have traversed right across the Luquillo Mountains. Of course, there have been many other near misses, and the 3 big ones that have hit have give us that kind of damage, as you see in the picture above the graph. So those are Hugo in '89, Georges in '98, and Maria in 2017. So big nitrate pulse comes out after each hurricane, and it can take several years to return to some sort of background, and that varies by watershed. I'm not going to talk about that. Next. Interestingly, the only other solute that we see with a response across the years has been potassium. This may be modified when we look in detail at the Hurricane Maria data sets, which we are in the process of doing. But basically, just like we saw with nitrate, we see a large increase in potassium after especially Georges and Maria, and a long time before we reach any recovery of potassium. So whether they're linked or not, we don't know, but it's an intriguing cross of biology and geochemistry that may be affecting this hurricane response. Next slide.
You have about 2.5 minutes, Bill.
So what's driving this response? We've done some hurricane simulation experiments where we cut branches of trees and place them on the ground like a hurricane does. And my part was to look at soil solution chemistry. Next slide. And what we see, the red line sums it all up, and we do the full hurricane treatment. A big pulse of nitrate comes out up to about 2 milligrams per liter nitrate N. So from that, we conclude, as well as other evidence, that the response we see in the streams to hurricane disturbance is in fact driven by the whole watershed and not by all the debris and changes in the stream channel. Next slide. Next slide. So finally, stream flow is a really important driver of concentration. Next slide. We plotted some data here from a paper in 2011 with our convener, Jamie Shanley. We're looking at the silica and the magnesium here compared to a pure dilution line. And we see that at the very highest flows, the silica actually achieves just a straight dilution at highest flow. And magnesium also has strong declines in concentration, noting the log scale in both these. Next slide. In contrast, dissolved organic carbon goes up at high flow, but then boomerangs around and goes down at the very highest flow. And nitrate is just not responsive to flow at all. The colors represent different eras with different concentrations after hurricanes. Next slide. So I'd like to acknowledge the many colleagues and students and technicians who contributed, the NSF, the LTER, the CZO, and individual grants, the USGS, the University of Puerto Rico, USDA Forest Service. These acknowledgements represent the challenges. How do we keep such a group together? How do we maintain institutional commitment? It's very difficult, whether it's with the USGS, we've struggled valiantly to maintain a research presence in Puerto Rico with the USGS. And so we're constantly fighting, trying to cobble things together because there's no central way to get this work funded at the scale we've been doing. Thank you.
Great. Thank you very much, Bill, and all of our speakers. So now we're going to move on to a general discussion. Please, audience members, do keep your points coming in. We would love to be able to get to them. I was going to start with one question that was posed really early on, and it was addressed to you, Theresa, about explaining what a gravimeter is, what it does, and the cost of it. But once Theresa's done, I'd be interested in other panelists chiming in about new, innovative, unique infrastructure that they may be installing at their sites to complement the long-term studies, and how you're integrating some very new techniques and concepts along with the older catchment infrastructure. With that, Theresa, will you tell us what a gravimeter is?
Yes. So these gravimeters are actually geodetic instruments. They weren't built for hydrologists and for the geologists. The hydrologic signal was a noise that they did not want. So that's when they contacted my colleague to get rid of this bloody noise in their time series. And from then on, people have started using them to actually measure that hydrological signal. And originally, they were used basically under lab conditions in buildings. But in the last few years, there have been companies building them in these field enclosures that you also saw on my slide. So you can actually now move them to the field. And they cost about 250,000, maybe a bit more. So they're not cheap. But the cool thing is that you can actually get the total water storage dynamics from them. I think there was a question if you can actually match that to the GRACE observations. So GRACE also observes gravity signals around the globe. The problem is a bit of the scale issue, right? Because the gravimeters measure on the scale of maybe a kilometer footprint, and GRACE is much larger, so you would need several to really match it. My colleagues are trying to now have something like a roving gravimeter, so you could actually measure at different points and then make that connection. That's the plan for the future.
So Theresa, 250,000 euros?
Yes.
Okay.
Does anyone else want to comment on new technologies being implemented within the existing watershed programs? And maybe eddy covariance could be brought up because Charu did bring up a question about that. So it'd be interesting to hear how that is being integrated into some sites. No one today?
I could comment on eddy covariance. It would be a really useful technique to have in catchments. The problem always is that with catchments, there's always terrain involved. And typically, eddy covariance works best on flat terrain. And I know places like Cover Brook have put in an eddy covariance tower, but there are some issues associated with getting high quality data from that. But I like the fact that people are kind of pushing the envelope and putting towers in some new places.
Yeah, CUAHSI, we've got a tower in really complex topography, and you do lose data due to sometimes the atmospheric conditions violate the assumptions, but it has been useful for providing some truthing to other measurements that we do. And we've also used them at the Savannah River site, which is still rolling topography, and there it's worked very well for us.
We're exploring but haven't implemented putting in place time-lapse electrical resistivity tomography to look at changes in water content in the subsurface. The technologies are there. It's just a matter in a place like Peru of being able to get it there and implement it and maintain it.
Anyone else?
Yeah, we are using ERT2 actually, and we have carried out a few surveys over time, and it's actually a good complement to groundwater levels and also soil moisture measurement over the ground. And I want to comment on the request by Julia about the use of complex three-level sensor. I'm collaborating with a colleague of mine, ecophysiologist, and she is using this kind of, well, let's say they call it innovative sensors that are very compact and relatively cheap and can be used to monitor some tree scale parameters. And these are called tree talkers. And I think that the name is pretty great. And they measure Sapflow through, well, traditional Granier sensors. And then they use dendrometers, which is just one ring dendrometer. And in addition to that, they also measure the deviation from the verticality, which would be maybe helpful more in urban settings for, you know, assessing the tree stabilities, which actually in Italy is getting an important issue in the urban green management. And then also the light transmitted through the canopy. There are different spectra. Now I don't remember exactly which ones, but this can be useful to actually understand different radiation inputs at the tree scale. And in addition to that, they are also measuring the stem humidity and some, let's say, weather parameters like temperature and air humidity, but at the tree level. So one of the interesting points is how to see how, for instance, topography or the position over the landscape is affecting the eco-hydrological or physiological response at each individual trees. We have installed these arrays of different sensors along three, let's say, lines or positions over STP slopes. And we are basically checking how the different trees respond to the positions over the hill slope, assuming that a position also reflects the water availability. For instance, trees can accept water, assess water or groundwater in the lower position near the stream and not in the upper part of the hill. Results are ongoing, actually. We'll see what happens.
Thank you. So moving from data acquisition to the other end of the spectrum of data management in QA/QC, Jason Leach is interested in what tools we use for workflow and managing data. And he mentions things like, for example, Aquarius, keysters, or self-built tools using Python, R, or MATLAB. So maybe that's a big question, but maybe we focus on either successes or biggest challenges facing each site. And we get just a quick round robin from each of our panelists or presenters today. Theresa, could we start with you since you were the first presenter?
Okay. So yeah, as I mentioned on my slide, that's one of the challenges. At a different site, we've tried Aquarius. It was a bit of a struggle. At the moment, we mainly use our own tools or programmed in Python or R.
Tomas, do you have anything to add on that?
I don't really think so.
Okay. Todd?
Just keeping things well documented. We do work for the EPA and they demand certain QA/QC standards. And so we have to abide by those. So that helps us keep that in order.
Jean? You're muted, Jean.
Yeah. Is your question referring only to the programs, to Python and so on, or other difficulties or challenges?
You can address whichever is topmost in your mind regarding data management issues.
The management issues for us is just to have continuous data series, I would say, because we are working in difficult conditions. And so our problems come much earlier than management, actually. It's for the measurement that we struggle the most, I would say.
Bill?
Yeah, I wanted to highlight for new techniques the variety of sensors, in the water, and I think coupling aquatic and soil sensors. And so that gets to, your 15-minute records of temperature, soil moisture, soil PCO2, stream PCO2, et cetera. And so those are challenging. And just to deal with the volume of data, of course, and then also to QA/QC. So we've been using some tools that we've built and that are on the HydroShare, and we continue to look at ways to better visualize, to do better QA/QC, these different data streams. But it's the sort of big data era I think, is the challenge. The 15-minute records, not just of flow, but of everything, is where we're headed. And it's going to be very cool, but it's a lot of learning and work.
Daniela, Rhett, Josh, or Beth, any comments on this?
Yes, this is Beth. I just wanted to add the importance of metadata. Like, for example, we also are sharing data right now in HydroShare and EarthChem databases, and just the time and attention it takes to documenting the QA/QC and how things were collected, where and when, to make it useful for the future for others is a big area of emphasis.
I would say that if you're going to maintain a big site with a lot of data streams, you have to have either a half-time or full-time data manager, and that's their job. Because if it's everybody's little side project, you're going to get a mess.
I just echo that in terms of, many of my research efforts have been student-driven, and getting graduate students to focus on data curation and data quality and data sharing is a challenge, partly because the incentives aren't there in the same way they are for students to get, other kinds of publications.
Daniela, any thoughts on that, or should we move on to another question?
Well, not really. Data management is always issue. We are just at the beginning of this adventure, and my other experiences from other catchments, it just takes a lot of time, efforts, and people, and funding people, and getting PhD students so that who actually can continue and carry over the job is not so easy. Manpower is one of my biggest issues for that.
I see Jamie showing up. Jamie, do you want me to ask another question, or do you want to wrap up? You're muted.
Go for one more question, Steve.
All right. So Jan Seibert asked a question that I would actually like to direct back to Jan Seibert, but we'll get the panelists to address it. His question is, are the catchments of today easier or harder to understand model than the snow-dominated ones from previous weeks? And there was one comment already in the chat about yes, no, and maybe was the answer to that question. I don't recall who said that.
Well, I'll take a stab at that because we don't have any snow. So it's obviously easy to work in Puerto Rico because we don't have snow. And yet there was a question in the chat about what's the accuracy of your stream flow at high flow? I mean, I showed you this these pictures of stair steps, waterfalls of, constantly moving down the mountain. And so this is an issue and a concern. USGS has worked really hard to try to improve the rating curves where we have it. But the answer is, I think the snow in many places makes hydrology a lot easier if you're talking about a Rocky Mountain single pulse snow melt. And Luquillo, as Julia Jones has led a paper on stream flashiness, and Luquillo is extremely flashy, goes all up and down. So I think the biggest challenge though is where it's the mix, where we have transitional, where we're gone from classic snow driven, and now we're gonna have ice on snow and ice on soil. And we're gonna have snow, and then it's gonna be 75 degrees Fahrenheit, and then it's gonna not be snow, then it's going to come again. It's, to me, that's got to be the most challenging situation, and that's why I work in Puerto Rico. I also work in New Hampshire, but.
Thank you, everyone. I think we need to wrap up on the questions. Let me just remind you that week 8 culminates in a community discussion, so keep your questions coming. Let them carry over from week to week. If you have something that's really in your mind, send it to Jamie, myself, Theresa, or Julia, and we will assure that it gets addressed or that we'll try our best to address it in leading up to the final week.
Yep, and look for a more formal way to post your comments. See you next week. Thanks for everyone.
Thank you. Great
Yeah.
presentations.
Thank you so much.
Really great job.
Thanks.
Thanks.
Bye-bye.
Take care, stay healthy.